I will repeat to have it on the record. So instead of this lecture, this last lecture, as it was supposed, we will have two shorter lectures today and next month, and only then in 2 weeks an exam for the Ukrainian participants. Please, can someone confirm that you can hear me?
Everything's okay.
Good, thanks. Okay, so today we will be talking about properties of parabolic equations associated with SDs and how to use them for numerical schemes. So assumptions that are going to be used through the whole lecture are as follows. We want our coefficients to be good, so Lipschitz continuous and of linear growth. Well, actually A2 follows from the second assumption here in a natural way. And I will assume that these functions, coefficients, are infinitely differentiable in x for every fixed t, and that those derivatives are bounded, absolutely bounded. This is actually what was used in the last lecture. I didn't state it perfectly clear, but this is the way differentiability of coefficients is understood in the previous lecture. Now, the function f small is k times continuously differentiable, and any combinations of derivatives, any partial derivatives of higher order, satisfies some polynomial growth condition. So this is multi-index, this is L1 times derivative with respect to x1, etc., etc. Our main object is this function, which is defined by this expression for some fixed t. And last lecture, I used to write two time parameters as subscripts and x as an argument, but we don't need it anymore, so I switched to more common notation, at least in our course, that xt is a starting point. It starts from x at time t, this process xi, and it satisfies stochastic differential equation with these coefficients a and sigma that satisfy those assumptions stated above. So the first theorem we have is as follows. If we fix t, this function as a function of x is exactly k times continuously differentiable, and, what is also very important, one can calculate the derivative of this function by formally pushing the derivative inside of the expectation. So this, since it's a multidimensional case, we need to take partial derivatives with respect to every direction here, and then we need to differentiate those components of our process. So this is just the full derivative. And this happens in the case of the first derivative, and the analogous expressions are available for higher order derivatives by just pushing additional derivatives inside. So you will differentiate this, etc., etc. So if we have a very simplistic case, so our process is one-dimensional, and this W is also one-dimensional. The dimension of W is M in our course. Then we have this simple formula. And actually no proofs, we will restrict our attention only to the case where this happens, and also almost, or maybe even in all the proofs, we will assume that the drift coefficient is just zero. The reason is that typically stochastic integrals are harder to work with anyway, and almost everything that works for stochastic will work for the drift part. And it just makes what we write longer. So let's prove this theorem. So step one is going to be as follows. Exactly as in the previous lecture, let us define this expression. It's Control Z. psi xt. And then we know from the previous lecture, it was established there, that the following representation holds. Integral from 0 to t dws Now, let us assume also, wait a second. Let's do it as follows. Simplify notation, let us assume additionally that sigma is autonomous. That is, does not depend on S. Then can be rewritten as psi xt. Because now psi x of t in this expression doesn't depend on S here and here. This is exactly x0 tau minus t. And we will denote psi x0 just by psi x. Then we can define. So this is our new time. Since time is fixed, in state of t, we can consider just tau t capital minus t. And then we can safely define. If this coefficient sigma is not autonomous, you can do pretty much the same, but you will need to take care of two indexed time parameters. Just not worth it. It doesn't add anything to the proof at this point. And at the last lecture, we use the following representation. Here I can now write from 0 to t safely dws eta xy of s integral from 0 to 1 du, and here stands sigma prime psi x of s plus uy eta xy of s. You can check that. Now we want to use pretty much the same idea but to the expression of this form, the derivative we really want. Psi x plus y t minus f psi x of t. To obtain this, this equals just eta xy of t integral from 0 to u du f prime psi x of t plus uy eta xy of t. So essentially what gives here, we just applied here, but for f instead of sigma. And now we want to prepare our passing to the limit. I will add and subtract a number of terms. Let us denote these expressions gxy of t. Gxy of t plus sigma prime x of t. Here integral from 0 to 1 du and u. It also depends on u. Maybe it's even better to write x, y, t, u. G, x, y, t of u. G, x, y, t of u minus just f prime psi x of t plus what is left. And we exactly have is, so this should stay in the limit and we should get rid of this term and the second term. For that, let us note step 2 that for any p belonging to the set of natural numbers, do I miss this? I think I need. Now, how to prove this? We have the equation for eta here. This is bounded. So this is whole integral is bounded. This is stochastic integral. And the function that is being integrated is eta xys times something bounded. So we can use this boundedness of the regional coefficients, the standard localization procedure, and we can derive by using some LP estimates of stochastic integrals the following in a standard manner. This constant is going to depend on t capital for obvious reasons, where eta and xy of t is just eta xy stopped at the in moment it hits the level. So it's just a standard localization procedure because you cannot just write this without this n capital, it might not exist. Now you use Graunow-Bellman inequality and the lemma fatu to conclude that this holds. So I will skip the details. Thus, we establish two facts. Firstly, this squared goes to 0 almost surely after choosing a proper modifications of our processes. But we can do this exactly in the previous lecture because all the calculations that happen in this proof happen for fixed x, t, t capital. So by changing modification, we do not change anything in those formulas. So this holds almost surely. And the family parameterized by y is uniformly integrable because it has higher moments. This has higher moments, this has higher moments. So this square also has the fourth moment, etc., etc. Oh, it has the second moment, the fourth moment for the original difference. Which means by the Lebesgue-dominated convergence theorem, automatically this converges to this when y goes to 0 in L2 omega. And this is what we want, what we are going to use on the next step. Step 3, we will return to I1 here and I2. So by the Cauchy inequality for I1, Cauchy inequality, we get mathematical expectation at x y t minus psi prime x of t squared 1/2. And what is left? Integral from 0 to 1 du gx y tu, everything squared, and 1/2. So I had to use this L2 convergence because here stands f prime, and f prime is not bounded, it's not supposed to be bounded. So this is now bounded just after integration, because this can be estimated in terms of some polynomial with respect to psi xt and eta xyt. And we know that psi xt has all moments, and we now know that eta has all moments. So this goes to 0 because the first factor goes to 0. And for E2, we have, again, by the Cauchy inequality, we get the part that depends on this. This is bounded now. And here, now, if we denote this, say, kappa xy, then kappa xy goes probability 0 again. Why? Because this f prime is continuous, so one could use internally dominated convergence theorem to prove that this happens almost surely, or in probability, and supremum over, say, some small ball of such expressions is again bounded exactly by the same reasons, by the reasoning that we just used. Then again, by the Lebesgue convergence theorem, we can conclude. Here, using the usage of the Cauchy inequality is not necessary, but it does help in this case. Exactly. Now, if we return to the origin, and put mathematical expectations here, we can actually obtain that in the limit we get exactly this. But this is exactly what we wanted. Here. This coincides with what is left after taking the mathematical expectation, passing to the limit with respect to y. Now, step 4 would be higher derivatives, but effectively, you just need to relabel everything and use pretty much the same reasoning. You have boundness and polynomial growth for derivatives of coefficients and function of respectively, and so on. We are not going to discuss this. We just make a note that higher derivatives can be investigated by pretty much the same calculations. We do use, one remark, the boundness of derivatives of sigma and a directly. However, there are methods to also establish such result in the case whereas they satisfy pretty much the same exceptions as f. So only cut time or 2 times differentiable with polynomially growing derivatives. Typically, it's done via a so-called the theory of L2 derivatives. And here you can see that the main technical step was establishing this. So effectively, we don't used in what followed that eta x y t converges to the derivative almost surely. We only use it converges to some good function in L2. And there is a whole theory of L2 derivatives. One can find the exposition, this theory in Friedman's volume 1 and in Geekman-Skorohod's stochastic differential equation. But you need, as far as I recall, to be a bit careful about the book of Geekman and Skorohod. I think when passing to higher order derivatives, you need to add something into the proof. It's been quite some time since I read it, but as far as I recall, you need to fill some gaps. One specific gap when you iterate those derivatives, which is an interesting moment because I think it was the first book that published the whole series, so it is quite understandable. Something might be missing. Now, proposition. Again, all the previous assumptions hold, and for any x, let's write it this way, limit, or maybe it's better not to write limit, but just h minus 1, mathematical expectation of psi x t minus ht minus f of x converges to a f of x when h goes to 0, where here and henceforward a is the corresponding second order differential operator associated with our SD. Sigma sigma star kg x d squared xk xg. So the first theorem worked with partial derivatives. This is about one-sided left derivative in time. So again, we consider only one-dimensional case with zero drift. So the step one is going to be by the eta formula. For fixed t and h. Such expression, I will denote them. This is exactly the expression we consider in the definition. Mathematical expectation integral from 0, not from 0, but t minus h to t sigma squared f second derivative calculated at the point x t minus h s ds. Now this expectation is well defined because this is well behaved. Now step 2, I want to make a change of variables in this integral. So let's denote g sigma 1/2 f2 prime. And I want to consider this, and the change in variable should be as follows. S should be t minus h r from 0 to 1. So ds is minus h dr. So this h will be eaten by our time change, and using the derivative to push expectation inside, we can get from 1 to dr mathematical expectation g psi x t minus h is cannot change, and here going t minus h t minus hr And that's effectively all. Now, I don't think I need to push expectation here. Let's leave it here. Now here, this 0 to 1 dr g psi x t minus h t minus hr t minus hr go almost surely when h goes to 0 to just gxt. Again, by the Lebesgue dominated convergence theorem, used almost surely. Prove it. I will give this a simple exercise. There is nothing really problematic here. And this family, I will denote it GH. And the family GH with respect to parameterized by H is again uniformly integrable. Integrable since mathematical expectation GH squared is going to be less than 1 dr. Here's the Subini theorem. Remember that I use it so well. Psi x t minus r squared, and this is less than some constant integral from 0 to 1 dr, 1 plus mathematical expectation of this expression to some power that depends on the polynomial that is used for f two primes, which is 4 some. So we can pass to the limit by the Lebesgue dominated convergence theorem, now used second time here. So this is like iterated dominated convergence theorem. Now we are ready to formulate theorem 2. Give it a title, theorem 2, because we are going to use theorem 1. And this function u that we defined is actually 2 times continuously differentiable in x and 1 time continuously differentiable in t. So, and these functions are continuous with respect to xt simultaneous. So I will write it as follows. And we actually establish the inverse version of the Feynman-Scott formula, but only for the whole space. This on Rd times 0t open, and uxt is just equal f of x. So let's start from the end. Step 1 is very easy. Obviously, just some kind of dominated convergence. That's effectively all. Step 2. Now, by theorem 1, we can use the previous proposition. The previous proposition required this function f to be sufficiently continuous, differentiable. And theorem 1 establishes that for fixed t, this holds. So we can use the previous proposition for fixed position, for fixed time. The previous proposition can be used for function that does this for fixed t. So we will get like one-sided derivative effectively. H minus 1, mathematical exploitation u psi x t minus h t t minus uxt. This is now our f of x. This goes, when h goes to 0, to a u x of t. This is first ingredient. The second derivative. By the Markov property of solutions of SDs, we get ux t minus h is mathematical expectation. By definition, just write down the definition. This. Let's write it as follow x, the same expression, but we will take the conditional expectation with respect to the filtration at time t, and by the Markov property we obtain that this is just mathematical expectation f psi y t when y is exactly psi x t minus h of t. So we leave from t minus h to t, and we use this value to calculate this expectation. But this exactly u of psi x t minus h of t t by the definition of u. This is it. Thus, step 2 actually means that h minus 1 uxt minus ux t minus h converges minus uxt when h goes to 0. Why? Because we now look at this and replace this by this, and we get minus here. Now, the next step would be the following claim. For fixed x, u, and all derivatives with respect to partial variables are continuous functions of t. It's not hard to prove. Effectively, it's again a combination of the previous reasoning, so I guess we can believe this. So why we need this? Because we need this to be a good function of t, and it requires a second derivative. So I will give this an exercise. It's not hard to prove, but it's some lines. Now, step 5. Now, for fixed x, u xt has, by step 4, a continuous left-sided derivative, which implies uxt has a continuous derivative in t. So if the derivative is very well behaved, and if one-sided derivative is very well behaved, it's actually a proper derivative. I will leave this like an exercise or an example of some useful trick. Alternatively, you can just do all the calculation from the previous steps for right-sided derivative, and you will get equal, etc., etc. But this is a nice trick, I think. For instance, I regret not using it in my last paper. We also claimed that this holds, that these derivatives are jointly continuous, but it's not hard to prove, so pretty much using the same calculations. Let's do some, I think, remarks. Using something similar to this technique, one can also establish forward and backward Kolmogorov equations for densities. But unless you go very deep into some probabilistic arguments, you will need to demand a lot from those densities. So we exclude this from our course, and a standard reference is, again, Geekman-Skorohod's stochastic differential equations, or if you want cutting-edge approach is Bogachev and co-authors Fokker-Planck Kolmogorov equations. The latter book treats Kolmogorov backward and forward equations for transition densities as equations for measure-valued processes. So it's quite analytic. Now, using pretty much the same technique, maybe with some additional estimates, one can actually prove that solution of stochastic differential equations are diffusion processes in the sense of Kolmogorov. I'm not going to formulate this result. Maybe you will need something additional like psi x t plus h minus x is less some constants h squared 1 plus squared, etc. But overall, pretty much the reasoning is built by using the same steps: Grunwald-Bellman, polynomial bounds, etc., and continuity. Now, one important feature of this result is that this result is formulated only on the whole space. One can ask whether it's possible to formulate the full analog of the Feynman-Katz theorem in domain. The answer is no. The reason is that if you recall the Feynman-Katz formula, it includes something like this: psi x t tau tau, where tau is the moment the process hits the boundary. So if you want to start with a probabilistic representation and prove that it satisfies the corresponding equation, you need to know quite a lot about the joint distribution of the position of your process when it hits the boundary and the time when it hits the boundary. It's actually a trivial question. So overall, when you try to use probabilistic tools to prove such analogs of the Feynman-Katz formula, this is where you get. You don't get much more. There are some exceptions to that. The biggest exception is the Malявin calculus that develops a whole set of tools for solutions on domains. And the situation is very different in the case of elliptic PDEs. Still, the existence by probabilistic tools for elliptic PDEs is typically still done by analytic methods, with the exception of the Brownian motion itself, because one can use some simpler arguments and symmetry-based arguments. And this actually is what we are going to do on during the last lecture in this course. And this is the part that cannot really fit in this lecture, and I really want to talk a bit about it. But for parabolic PDEs, probabilistic tools in the terms of PDE theory are used not for an establishing the existence, but for discussing, for instance, boundary behavior of solutions, for numerical schemes and so. Now we want to use to make some usage of the results we obtained, and this is weak convergence for Euler-Maruyama and Milstein schemes. Let us recall the Euler-Maruyama. I will not discuss the Milstein scheme in this lecture at all, but except for the formulation of the corresponding theorem. So let us recall the Euler-Maruyama scheme. I will need T and K equal K divided by N times T for K from 0 to N, and N is a natural number. W and K is just WT and K plus 1 minus WT and K. And then the solution of txt. So again, I drop the possibility of it starting at any time. It just starts at 0 for simplicity. X of tt dwt is approximated, is modeled by at time t capital, and eta and n is defined in a recurrent way by the following equation: t eta nk t nk t divided over n plus sigma eta nk t nk delta w nk. And we start from just x, and this is true from k from 0 to n minus 1 to make it so it makes sense. The Milstein scheme includes one additional term, which is the iterated stochastic integral. Now, what is the weak approximation? The weak approximation is that for some function, instead of taking this value, we take this value. Now, if f is, say, Lipschitz, we can use the result for strong convergence of the Euler-Maruyama scheme to conclude that the error of this scheme is of order 1/2. But quite a fascinating fact is that actually, because we don't need to model the whole trajectory, which is highly irregular, we can get much better results for weak schemes. And the theorem, which is our last result, and it's called the Talay-Tubaro expansion, is as follows. So, given all the previous assumptions that we have stated in the beginning of our lecture, we have the following representation of this error. This is t divided over n times some mathematical expectation of some functions that depends on psi x of s and s ds plus something in terms of x, the starting point, divided by n squared, where Pn of x satisfies this estimate for some positive p. And this function can actually be calculated explicitly. In the terms of u, a, and sigma, and their derivatives. You can have slightly different representations of this function. In particular, I will just write it in one-dimensional case because this is the case we are going to work with. If everything is one-dimensional, this function is actually minus minus 1/2 a squared, this plus 1/2 a squared sigma xxx plus 1/8 sigma 4 d4 with respect to x 4 times plus 1/2 second derivative with respect to time plus a mixed derivative plus 1/2 sigma squared, again mixed derivative. And this operator is applied to u. Next. The same result is true for the Milstein scheme with different phi. So while the Milstein scheme is more accurate as a strong scheme, it has the same order of convergence as a weak scheme. I think the book of Claudin and Platen contains an example where I actually investigate the case when the Milstein scheme is worse than the Euler-Maruyama scheme as a weak scheme, and they explain in terms of this phi directly. So this actually has value, the possibility to know this error exactly, because this gives quite nice ways to estimate it. Now, as usually we have something that depends on t, but typically this grows exponentially at t. The reason because the Gronwall Bellman lemma will produce exponential terms in t when you will use them. So, there is this analog of this expansion for problematic f, discontinuous f. It's done by the tools of Malявin calculus by pushing derivatives from this function onto derivatives on this function from f, because previously we pushed all derivatives on f here, for instance, here. And Malявin calculus pushes those derivatives onto this density. It's a much harder result. It's also established by one of these authors as the second co-author of that result is different. So I'm not going to give you a full proof because it's lengthy, but let's discuss the idea and main steps. Step 1. This is a standard trick. We want to consider this minus this. This is what we care about. And this can be written minus, just by the definition what this is and what this function is. And now we can write this as a mathematical expectation. Because phi also is related to u by this. Here. So both sides are now written in terms of our u. And now we can write this as a sum from k from 0 to n minus 1 as a telescopic sum. Mathematical expectation u eta n k plus 1 tn k plus 1 minus u eta nk tnk, and I will denote such terms as I and k. Let us consider one term in the sum. For that, let us introduce an auxiliary process with continuous trajectories, which is a continuous version of the Euler-Maruyama scheme. We already considered it in our course. This process on this interval is defined by writing eta n of t equals eta nk plus integral from tnk to t sigma eta nk. I will consider only autonomous case also. DWS. Now, by the eta formula applied to this continuous process eta n of t on tnk plus 1, because this process was introduced by us exactly for the possibility to use the eta formula, because you cannot use the eta formula, applies the eta formula to the original scheme. It's discrete. I and k now equals mathematical expectation integral t and k tn k plus 1 ds plus a eta and k. Let me write this and we will explain this. Thanks, eta n. So, first of all, we use eta formula to this expression. So eta n k plus 1 tn k plus 1 is equal to u eta n tn k plus 1 tn k plus 1. So this is our function of eta n tn k plus 1 tn k plus 1 at this time. You need to be a bit more careful at this, because this representation changes to the representation on the next part of your interval, of your division of the original time interval, but since it's continuous, it doesn't matter. And this function, when s is equal to tnk, is exactly eta nk tnk, just by substituting tnk here. So this is exactly the beginning, the initial value of this function on this interval. And the eta formula states that what is left is the result of this form. So the expectation gets rid of a stochastic part. So we have just this derivative plus special derivatives. But because these coefficients are frozen, this is a typical way people refer to this operation. This is frozen. They say that A and K, which is in our case A dx plus 1 over high sigma squared eta nk d squared xx, has so-called frozen coefficients, because this is exactly the coefficients that appear in the eta formula for this process. And we already use it in our course calculation. So we have this expression. And the idea is to use the eta formula 2 more times to produce this phi and something that is left here. Now, again, for simplicity, I will assume that we do not have any drift. So I will just write it in this way. It's just 1/2 sigma nk squared d squared xx, where sigma nk equals sigma eta nk. And a is just 1/2 sigma squared, is a proper differential operator in the sense that this is a function of x too. So you differentiate with respect to x and multiply by the function of x. Now, u is a solution of the corresponding parabolic equation. So instead of this ds applied to u, I can write just a, because this happens. Since this, one can write tnk plus 1 a and k minus a applied to u xs, and then x equals to this ds. Now, as I said, if we're going to iterate, this will produce if we are going to use the eta formula 2 times, this will produce eventually by just the way eta formula works, something like this, mathematical interpretation of some function that is going to depend on this. And this function is going to be given in the terms eta and k, derivatives of coefficients, derivatives of the original u, etc., etc. But this is going to be bounded, at least locally. And this is going to give you 1 over n squared. And you have n such terms. This will going to give you 1 over n. It is of the third order, negative order. There are n such terms. So this is how you get this part. And again, it's certainly locally bounded, as I said. So we need to understand why we get here exactly this. Since we have t over n and we have sum, so this difference i and k should be of the second order. But let's do some calculation to understand how we find that function phi capital. We have this uxs. This is just sigma squared eta nk minus sigma squared x. There is no drift, so it's very simple. Let us introduce a new function by just setting. Then I and k is, again, let us rewrite it one more time. tnk plus 1 g eta n s as ds. So now we use the eta formula here to this function g. At mathematical expectation g eta n s. I will write this s1 to prepare us for this iterated integrals. s1 is mathematical expectation, say xs, when x is on the left hand side of our interval and s is equal to tnk, plus integral from tnk to s1 ds2 plus a, again of this form, applied to gx s2 when x equal eta n s2. Now, this is just 0. Why? Because we're going to substitute in this expression something, and x is going to be equal eta and k, but this is just 0. So this is why we have at least second integral of this decomposition. This is exactly what we had, what we are going to have. So we have just this term, and here let us see what happens inside. N k d squared xx, and this is going to be applied to g, and g is already of this form, nk minus sigma squared x ux s2. So let's see what happens here. This part doesn't depend on s2, so I just push everything inside. And this will result in a mixed third derivative plus this 1/4, right? Sigma fourth and k fourth derivative ux plus this multiplied this, which gives us minus 1/4 sigma squared nk xx sigma squared x d squared xx ux s2. I apply this operator to this part. Now, the trick is dtu is actually minus u. So, if you look at this part, 1/4 sigma squared nk xx sigma squared x xx ux s2 is formally, I don't care about dividing by sigma squared x, it's not going to matter. In the end, 1/2 sigma squared x d squared xx, and here stands again 1/2 sigma squared x d squared u. I just divided and multiplied by this, but this is exactly a squared u in our case. So it's just minus sigma prime k and k and k and k divided by sigma squared x. And here stands just derivatives with respect to time. Applied to the first, to the result of application A once, which is 1/2 sigma squared x xx ux s2. Now this cancels, and we get minus 1/2 and k, and again mixed derivative xx ux s2. Now this part cancels with this part. So the result is minus 1/2 sigma squared x mixed derivative t s2 xx ux s2 plus this term 1 force sigma force nk x u x s2. So if you are going to use the eta formula one more time, this will produce as sigma squared, the third derivative at x equals eta nk. And this will give us something into our phi capital, and this will give us something into phi capital. We need to apply the eta formula to this part. This will give us the fourth derivative of the expression at x equal to eta nk. Now, if we compare this with the original phi, we don't have drift. So this doesn't exist, this doesn't exist, this doesn't exist. We have three terms. This, we already got it. And this is actually, again, is a part of this. Why? Because of the tricks dta u equals minus a squared u. So you can take the part from here and obtain this part. If we had considered drift, it would have been more complicated and would be a bit more natural for this part to appear. We would not have been able to get rid of it very easily. But since we considered simplest calculation, it got hidden in this part. The only problem that I see is that I somehow got wrong coefficients. We get additional 1/2 from this part, but we have something like sigma squared of x, this s2 x u x s2 is going to be 2 ds2 au, which is going to and this is again minus d squared s2 s2 ux s2. So this is how we recover this second derivative, but still, I guess I lost 1/2 somewhere. Or maybe I had this written in the proper way. Or maybe I'm missing something. Whatever. The idea is here, so you do such decomposition and you play with this, and the dt equals minus a when applied to u. So effectively you can rewrite somewhat this phi in different ways. Now step 2 would be as follows. We need to work in such a way that the result contains this integral. And obviously it can be obtained by doing such things that this is quite small. It is sufficient to have that this function is continuously differentiable on 0t for fixed s, fixed x. You can prove this by using an analog of the proposition we used in the previous part of our lecture, but in our lecture we didn't have this S here, so we had just the second order differential operator in the right hand side. I mean this. Not this, but here this proposition. You will get not only A, but also the part that consists of time derivative. But overall, it's pretty much the same calculation with the same idea, so we are not going to do it. And if we have a continuously differential function, it's very easy and almost immediate to see this holds. Now we need to combine these two steps. So step 3 is going to combine by step 2 our error plus or something small, sufficiently small is actually even smaller. No, it's of this order. So now we want to approximate this sum by this integral. So it is sufficient to show that T minus y psi x t and k is it's effectively just sufficient that this is supremo and locally uniformly in X at least. Why? Because we have already one here. No, we do not, right? We need a stronger, slightly stronger statement. This is this. Then the error when we replace these terms with these terms is going to be of order n minus 2, and we will require t minus n times the integral. Now, for that, the idea is to use pretty much the previous theory, but now by introducing functions f and k, which is going to be x, t, and k, and this is going to be the function of the same time as f original. And u and k are going to be solutions of the parabolic equations that correspond to this psi x, but you will need to do something like that. So you will apply pretty much the same decomposition on every k up to time t and k. And if you develop such part of the theory for your parabolic equations with parameters, this is going to play the role of the parameter. You will get good polynomial bounds of this error, and by using again step 1 exactly, and you will finish the proof. It's quite lengthy, so I will refer to the original paper or say Graham Talay for the discussion of how to do it properly. But overall, it's pretty much the same. You just need to be careful when writing down this. And using this step 1 for such functions up to time t and k, etc. So in the end, you will get this result. And this is all for today. Does anyone have questions? Good. Then I will see you next time for this time for the last lecture because I don't have any
And what are we going to talk about?
We're going talking about elliptic equations and regular points, effectively.
Okay, thank you.
You're welcome. And that's all for today. Good luck.
You too.
Thank you.